Hello everyone, I welcome you again in this course Introduction to Sequence Stratigraphy. I am Biplav Bhattacharya and today we are going to discuss on the correlation concept, correlations in stratigraphic successions. This particular concept is very important because when we are looking into sequence stratigraphic framework, we commonly consider the entire basin scale succession, and for applying the sequence stratigraphic concept, it is very important to know that what are the different units, how they are laterally distributed and how they are temporally distributed across the entire basin. As in the previous class we have seen that concept of scale. So, for identification of different units of different orders, we first have to know exactly in a very clear way that how these different units are occurring across the basin. And to know that, the primary tool that we have is the correlation of different logs, different vertical successions. So, correlation is a very basic concept, very basic tool in stratigraphy. I hope that many of you already know about correlation, but as part of this particular course, I am just introducing you with this particular concept. So, let us start with one example over here. This is one section we have recorded from the subsurface data, where we are getting different units, different rock units and different features, geological features which are present in this particular section, this particular area. So, in this particular profile section, if I ask you to arrange these in terms of their occurrences from the oldest to the youngest. So, basically what you will do, you will try to apply the concept of relative time. So, you will try to identify the relative time of events and you will try to reconstruct them in order of their occurrences. So, what we are getting over here, if I try to reconstruct, I know you can also do that, just let us do that. So, what is the first event over here? It is either E or G. So, there is no direct information given over here that which one is earlier. So, we can have either one, either E is the basement and on that a sedimentary unit G has deposited, or maybe G was the original unit and then E as a batholith has intruded. So, E or G is the primary unit. Then that has been affected with a fault which is 2, marked here as 2. After that we have an unconformity, and on that unconformity the sedimentary units, sedimentary beds K, D, L, A and M, they are deposited one after another, and once they are deposited, then they have gone through some sort of folding, and then that folding is affected by another phase of unconformity, and on that unconformity what we are getting is unit B and unit I, again sedimentary rocks. These units are then affected by an igneous activity, igneous process. So, that igneous process is the emplacement of the igneous body O, which is covering up to the unit I, and after that this entire succession has been affected by another fault which is marked as 1. After this process, what happened? Another unconformity. So, there is another break, and that break is overlain by again sedimentary units H, C and F, and after this deposition of H, C and F, this entire unit is faulted by another fault, the last fault in this particular section, which is marked as 3, and after that, after this faulting, the final event in this succession is the emplacement of another igneous body which is marked as N. So, so many events are there within this small section, one event after that another event, and each of them have their own significance and have their own time intervals, and we can understand or reconstruct these time events with respect to each other, which we call as the relative time, because here we are not determining the absolute time or the actual time involved over here. We do not know what is the age of these rocks, what is the age of emplacement of this particular igneous body, we do not know that. But what we can do is we are just placing one event or one rock body above another one with respect to one another based on their mutual relations we can observe in this particular section. So, this is the reconstruction of the relative time of events, and when we are doing that, very commonly, knowingly or maybe unknowingly, we are applying some basic principles of stratigraphy. These are some very fundamental principles of stratigraphy which I think all of us know about that. So, first one is the principle of uniformitarianism, which says the present is the key to the past. That means all the processes going on today, the processes that we can observe today and their products used to happen in the same way in the past. So, present is the key to the past is the basic statement for uniformitarianism. However, that may not be true always, particularly if we go back to the geological past. This particular concept, this particular idea does not hold true for all instances, because in the earlier ages, particularly when you go back to the Precambrians, there the processes were not exactly the same, the earth conditions were not exactly the same. But anyway, this is a very basic fundamental concept. The second concept, the principle of superposition, which says that in an undeformed sedimentary terrain, the older rocks will be overlain by the younger rocks. So, when we are doing this kind of relative time arrangements, this concept is very important, because it directly says that always the underlying unit is the oldest one, the overlying unit is the younger one, until and unless there is some reversing of the beds that may be caused by folding or thrusting. So, the basic condition is we can apply this in an undeformed bed, undeformed succession. So, this is a very fundamental principle. Principle of original horizontality, which says that the sedimentary beds are originally deposited in an horizontal fashion. If I refer back to the earlier diagram, there we can see that several units are appearing like this. So, if I refer back to this particular principle, the principle of original horizontality, where we know that the sedimentary units are originally deposited in a horizontal fashion. So, they cannot get deposited like this. So, definitely there is some event, maybe a folding has occurred over there, and definitely that folding is succeeding the deposition process. The fourth one, principle of original lateral continuity. So, this principle says that in a succession of strata, today maybe we are getting those strata in the outcrops or maybe in subsection as discrete separated units, but originally when they were deposited, they were laterally continuous. So, maybe today you are getting one succession over here, another succession over here, which are laterally apart by maybe 100 meter or maybe 1000 meter. But as per this principle, it says that these units originally were together. Today they are appearing as separate units because maybe some erosion has occurred, maybe some other event has occurred in between that. Maybe some faulting has occurred, maybe some folding has occurred, maybe some simple erosion has occurred, maybe a river is flowing through that, a valley has formed, and that is why these units are today appearing as two discrete units. But originally when they were deposited, they were continuous and they were deposited like this. So, this principle of original lateral continuity is the basic principle for correlation. Principle of cross-cutting relationships, already we have applied that in our last diagram, where always one rock body which is cross-cutting the others is younger with respect to the host rock bodies. So, whenever we get a cross-cutting relation, the unit which is cross-cutting the others is the younger one with respect to the host rocks. That already we have applied in the previous diagram. Next one, the principle of inclusions. So, this particular principle says that whenever you get an inclusion within a host rock, the inclusion is older with respect to the host rock. So, for example, if you are say you have one sedimentary unit, sedimentary body, a sandstone, and within that maybe some igneous rock body has intruded. So, what you are getting now are some remnants or some units of this sandstone body present within this igneous body, the protoliths, original host rock. So, what you are getting within this igneous rock body, you are getting some inclusions of sandstone. So, sandstone is older with respect to the host rock. It can be the reverse. Maybe you have one basement rock and this basement rock is eroded and clasts are formed, and then you get a conglomerate deposited over here where clasts from this igneous rock body are present within this sandstone or this conglomerate. So, what you are getting now, this is the host rock which has formed later, and within this host rock you are getting remnants of this original older rock body. So, the inclusions are always older than the host rock body. And the last one, principle of faunal succession. This is a very important principle which says that in a succession of strata, again undeformed strata, we commonly expect relatively less evolved older forms at the bottom and more evolved younger forms towards the top of the succession. So, this goes along with the principle of superposition, where we are saying older rocks at the bottom and younger rocks at the top. So, at the same time, if we look into the faunal assemblages, there we can expect relatively older and less evolved form, less evolved taxa to be present within this older rock near to the lower part of the succession, and as you move up across time, there you get more evolved and younger forms within the younger bits. So, these 7 are the basic principles of stratigraphy which help us in reconstruction of the relative time scale, and very often knowingly or unknowingly we are applying these principles whenever we are doing any work in stratigraphy or any work in terms of correlation or any work in terms of basin analysis, reconstruction of the paleogeography, reconstruction of the paleodepositional environment, etc., etc. So, these principles are very fundamental and very important. So, based on these principles, we can now discuss on the stratigraphic correlation, where correlation is the procedure to demonstrate the correspondence of the geographically separated parts of a particular geologic unit. So, just recall back the concept of the principle of original lateral continuity. So, correlation is just the application of that, and when you are applying that particular concept, when you are applying that concept of lateral continuity, there you have to apply the concept of relative age in terms of older versus younger rocks. Maybe in one area you can have several sandstone units which are separated by mudstone. So, you cannot correlate any sandstone with another one, with another outcrop. You have to get idea that what are the relative time scale and which sandstone you have to correlate. So, it can be based on some basic tools depending on what is our purpose and also what kind of information, what kind of data is available with us. So, it can be lithocorrelation, where we try to link the similar lithology in terms of their stratigraphic position, definitely the relative stratigraphic position, or sometime we can use the sequential or geometric relation, particularly when it is a lithodemic unit. We can have biocorrelation, as the name suggests, it is based on fossil assemblages or fossil content. So, based on the biostratigraphic position, and they help us to identify the biostratigraphy many times. Very often we do this together, lithocorrelation and biocorrelation together, to get a better result, more convincing result, and we can do chronocorrelation as well, where we try to correlate in terms of their correspondence in age. So, basically when we do the correlation in practical aspect, there we apply all these 3 approaches together, because there we have to consider the relative ages of individual litho units, as well as we have to correlate in terms of their similarity, and that similarity may be lithological similarity, may be biological similarity, or both, and their correspondence is matched in terms of their position in the relative time scale. So, in actual practice we apply these 3 approaches, these 3 methods together depending on the data source which is available to us. So, let us take one example. These are some random examples that I am showing you just to give you idea that what kind of correlations we can make. Say you have several logs available to you from one area, and there say this is log 1, 2, 3, 4, 5. These 5 logs are occurring in one plane, or rather in that area. These are some random logs that you have made, where you have recorded the distribution of different rock bodies, which may be based on outcrops or maybe from subsurface data, and you are arranging them in one line. So, you are getting 5 such logs arranged in one line, and you are trying to correlate them in terms of their lateral occurrences. So, as you can see over here, this is one sand body which is the major sand body that has been correlated. At the same time, you can get another section where you are getting 1, 2 and 3, these 3 logs, they are in another section. So, basically what you are doing, you are trying to correlate them in 3 dimension. And in practical aspect, we have to do this kind of correlation in multiple sections together to get a 3D distribution of the different phases types. So, until and unless we know the actual 3D distribution of different phases types, we cannot understand the distribution of the depositional systems, and we cannot interpret about the systems tracks or the sequences. So, when we are doing this correlation, this is simply lateral continuity that we try to demarcate of certain marker bits, and based on those marker bits we can correlate the overlying and the underlying units. And when we are trying to demarcate these lines, when we are trying to demarcate this correspondence between these individual marker litho units, there we are trying to apply these basic stratigraphic principles. So, in lithostratigraphic correlation, what we commonly do, say for example, in this case we have a common base for both these units, both these logs taken from area A and area B. We are getting similar correspondence over here in this part, we are getting similar correspondence over here in most of the lithologies. But as you can see over here, their vertical thicknesses, they are not matching, they are varying. Now the question arises, why these are varying? This is very common thing, because if you think of a depositional basin, the basin configuration, its bathymetry is not same throughout across the basin. So if you just consider about one basin, it is just going on like this. So if you are getting a log from somewhere here and you are getting a log from somewhere here, where the entire depositional succession is this much. So definitely the thickness of one unit, one particular litho unit, say for example this limestone unit, may not be exactly same as over here. Thickness of this particular sandstone and this particular sandstone may not be the same, because the conditions here and here, they are different. The depth conditions are slightly varying, but they are time correspondent. They are deposited at the same time. So for doing lithostratigraphic correlations, what we commonly follow, there is a continuous lateral tracing of the lithostratigraphic units. That is the most important part. So we have to continuously trace laterally in between two successive logs how one unit is continuing. For example, over here again I am taking this limestone, this is a limestone, this is another limestone, but there are certain variations. So in terms of depositional conditions or depositional time, we have a limestone depositing condition in both these areas. So they are continuous. But when I am going to the detail in terms of their lithological similarity or dissimilarity, I am getting a mismatch, and that is why I am pointing out over here that they are not exactly contemporary. There is a change in the phases. Though it is a limestone depositing condition prevailing, but from this point to this point, there is a change in the depositional condition and we are getting two different phases, though overall it is a limestone depositing condition. And that is further supported by the underlying and the overlying beds, which are exactly the same. So that means that the conditions in these two areas were almost same. Only what has changed is the thicknesses across time. In one of our previous class, we were discussing about the stratigraphic units, and where we are discussing about the diachronic units. So many a times during this correlation, we get certain litho units which are cross-cutting the time planes. As you can see over here, this limestone unit or maybe this cell unit, they are cross-cutting the time planes, because in this particular diagram, always the time planes are horizontal. So lateral tracing of the lithostratigraphic units is the key procedure, key tool for starting the lithostratigraphic correlation, where we try to correlate or we try to establish the correspondence between individual units. And when we are trying to do this lateral correspondence, there we try to emphasize on the lithologic similarity and the stratigraphic position. So this I have already given you the example. The stratigraphic position means, for example, over here in this unit, this limestone unit is overlain by a sandstone, mudstone or sandstone heterolith alternation, and it is underlain by a cell. When I am looking into log A, here also it is a cell which is underlying and a sandstone heterolith alternation occurring at the top. So the limestone units are not exactly same, but due to this stratigraphic position, the underlying and the overlying units are same. So due to this stratigraphic similarity, lithologic similarity, we can trace them laterally, we can establish the correspondence between these two units as they were laterally continuous in terms of their time of deposition, conditions of depositions. Lithostratigraphic correlation can be established through well logs, and nowadays it is done through softwares also, where we can get a very high resolution correlation of these lithostratigraphic units. So, correlation by well logs can give us much better idea, much better picture about the subsurface condition. So, lithostratigraphic correlation straightway gives us idea about the lateral distribution of different litho units, and many times these litho units are nothing but different facies or assemblages of facies or maybe the depositional systems. So, through lithostratigraphic correlation straightway we get idea about the distribution of different depositional systems across the basin. But for that purpose, what is required? We have to correlate several number of logs, because these logs, say for example, when I am saying this particular log from area A, this is just representing one small section, it is not representing the entire basin. So, from one basin, say if this is the entire basinal area, so this point A may be representing only this part. What about the other portion? Say this area B is over here. So, when I am making a correlation between A and B, I am getting this particular section. But what about the other portions? So, we have to take logs from other portions, other areas, and we have to make correlations like this, like this. When we make correlations like this and we make a correspondence through all these sections in between these litho units, what we get is the 3D distribution of the depositional systems, which is required for sequence stratigraphic study. So, lithostratigraphic techniques involve the relative age of the rock, indicating which rock units are younger or which units are older, so that we can do the correlation on the basis of lithological characteristics, but it does not provide a particular time framework for stratigraphy. Here in case of lithostratigraphy, we are just identifying the relative time. In stratigraphy, what we require is the absolute time scale. So, we are placing them in terms of relative time. So, it is a bit of chronocorrelation, but it has no direct implication on the time scale, stratigraphic time scale or geological time scale, and we cannot apply that particular concept through lithostratigraphic correlation. So, that is one limitation of lithostratigraphic correlation. If we look into the biostratigraphic correlation, it has certain advantages over lithostratigraphic correlation, because here we deal with the fossils, fossil contents within individual rock bodies. And when I am saying the rock bodies, definitely the characteristic properties of the rock bodies are also involved over here. So, biostratigraphic correlations are not only the biostratigraphy, not only the fossils, it is the lithology, and along with the lithology we consider the fossils. But if fossil contents are very dominant, sometimes we can ignore the lithological part as well. So, when we are trying to correlate in terms of fossil content, the factors that we consider is the abundance and size of the fossils, the degree of dispersal of the fossils, the preservation potential of the fossils, and the rate of speciation of the fossils. This will control that what will be the distribution of different fossils in different stratigraphic units. Based on that, we can define different zones like assemblage zone, like interval zone, like the acme zone, and individual zones can be used for the interpretation or correlation of strata. So, when we apply this concept, it comes under the biostratigraphic correlation. So, this is one example of biostratigraphic correlation where we are correlating in terms of assemblage biozone. So, as you can see over here, several assemblages are depicted in two different logs A and B, and based on their positions, irrespective of the lithology, we are correlating them. But many cases, as you can see over here in this particular unit or in this particular unit, the lithology appears very much same, because commonly the assemblages of fossils are contained within similar kind of rock strata. Similar kind of correlation can be done based on the abundance biozone. So, a particular taxon showing abundance to its maximum in different areas in different times. So, we can correlate based on this abundance zone between area 1, 2, 3 and 4, and that can give us idea about the distribution pattern of a particular taxon, how it has evolved through time. So, this kind of correlations are often useful for identification of particular global event. The third one, another example which is based on the taxon range biozone or interval biozone. So, again here we have two sections, section X and section Y, and in this case we are taking, say for example, the interval of E and F, interval of D and E, which are correlated over here. Similarly, we are getting the range of C, for example, the taxon range, taxon C, its range, and based on that we are making this correlation. So, any of these two tools can be used, either the taxon range biozone where we are getting distinct taxon and we are using their range of occurrence as the tool for correlation, or sometime we can use the interval of appearance or interval of disappearance, and we can use them as the tool for correlation. So, in biostratigraphic correlation, these are the different ways we can use the biozones for correlation purpose. And since fossils, particularly certain fossil types, they have some age connotations. So, biostratigraphic correlations often lead us to certain age connotations. They have much better age connotations with respect to the lithostratigraphic correlation. So, here in this case also, when you are doing biostratigraphic correlations, it is not independent of chronocorrelation or lithocorrelation. And for a better or convincing result, in practice what we do is application of these three tools together for getting a 3D picture of the distribution of different litho units, different depositional systems across the basin. So, these are some of the references, some of the books that you can follow for much detailed reading on this particular topic, and with this particular concept of correlation, we will move on to the next topic where we will discuss about the cyclicities in sedimentary successions. So, thank you everybody.